Okay. Here's a quick review. If you have two non-degenerate eigenfunctions of a Hermitian operator, you can prove that they're orthogonal. Actually, we already did this proof before, and this is just a review. Let's say f1 and f2 are non-degenerate eigenfunctions. What do we mean by non-degenerate eigenfunctions? They have, non-degenerate means they have different eigenvalues, right? So in this particular case, operator A applied on function f1 gives you back a constant times f1, so that constant is your eigenvalue, right? So a sub 1 is the coefficient, is the eigenvalue corresponding to eigenfunction f1, and we have here A applied, operator A applied on function f2 gives you back a constant a2 times the original function f2, so we say a2 is the eigenvalue that corresponds to eigenfunction f2. Now, when do we say f1 and f2 are non-degenerate? If a1 is not equal to a2. That's what non-degenerate means, right? And you can prove that f1 and f2 are orthogonal. What does orthogonal mean? That means f1 star f2 d tau, the integral of that must be equal to 0 for f1 and f2 to be orthogonal. Okay? So A is Hermitian, so that means this integral right here, if we have f1 star a hat operating on f2 d tau, if you flip the roles for f1 and f2, so you put f2 here instead and f1 over here, and take the complex conjugate of the integral, that's the definition of a Hermitian operator, right? So this equation is implied if A is Hermitian, right? In fact, f1 and f2 don't have to be eigenfunctions of A if A is Hermitian, as long as they're well behaved. All right, so how are we going to prove that they are orthogonal? You remember? Let's start off with a hat f1 equals a1 f1. Okay. Let me rewrite this way. a1 f1. Let's multiply both sides by f2 star. Okay. And then integrate both sides over all possible space. So integral d tau, integral d tau. Okay. So let's simplify this. What's a hat f1? F1 is an eigenfunction. It gives you back a constant a1 times f1 d tau. And you have f2 star. And what do you have on the other side? I can pull out my a1, right? I have f2 star f1 d tau. Now we're proving that that integral is going to be equal to 0, right? So let's move everything to the left. I can simplify this one on the left. I can write that as a1 integral of f2 star f1 d tau. So I'm going to move this one over here to the left. So I'm going to write minus a1. Oops, hold on. What did I miss? Okay, what did I miss here? It's the same thing. The whole thing is equal to 0. Okay. Oh, sorry, I forgot. Let's start off with this equation right here. Okay, backtrack. Let's backtrack. Sorry about that. Let's start with the definition of a Hermitian operator. Okay, so integral of f1 star a hat f2 d tau, this left-hand side right here, what's that equal to? It's going to be f1 star a2 f2 d tau, correct? So if I apply operator A on f2, that's what I'll get. And this thing on the right-hand side is equal to the left-hand side because A is Hermitian. So that's going to give me f2 star. What's a hat applied on f1? Gives you a1 f1 and d tau. And then this whole thing on the right-hand side, we have to take the complex conjugate. All right? All right, so what do we have now? We can simplify this. We can say that we can factor out a2. So we have on the left-hand side, you have a2 times the integral of f1 star f2 d tau is equal to, I can factor out my a1, but no, look, that has to be a1 star. You have to factor out the complex conjugate of a1. So a1 star integral of f2 star f1 d tau, but this whole thing must be complex conjugated, right? Okay, let's further simplify the right-hand side. What do we get? Well, we've already proved earlier that eigenvalues of a Hermitian operator are real, right? So I can just rewrite a1 star as a1. But what is the integral of f2 star f1 d tau? What is f2 star star? That's just going to be f2. What is f1 star? That's f1 star d tau. Okay? So I have the left-hand side right here is still a2 integral of f1 star f2 d tau. I'll move everything to the left now. What do I have? a2 integral of f1 star f2 d tau minus a1 integral of f2 f1 star d tau equal to 0. Okay? Let's put this in bracket notation to make it easier to see. This is going to be what goes in the bra. F1 in the bra, F2 in the ket. So that's A2 bracket F1, F2 minus A1. Let's put this in a bracket. Which one of this is starred? So that's the one that goes in the bra, right? You can think of it this way. F2, F1 star, that's the same thing as F1 star, F2, right? So F1 goes in the bra, F2 goes in the ket, and that thing is equal to, the whole thing is equal to 0. But remember we said A1 star is equal to A1 because we've already proven that the eigenvalue is real for a Hermitian operator. So you can factor out F1, the bracket F1, F2. So you have A2 minus A1 times F, the bracket F1, F2 is equal to 0. Okay? Product of two things is equal to 0. That means one or the other or both are 0, right? But what do we already know? This is not equal to 0 because we said that we have a non-degenerate eigenfunctions, right? So if that first factor is not equal to 0, then what did we just prove? That F1, F2, that bracket integral right there is equal to 0. And what we just did was prove that F1 and F2 are, what's the word? Orthogonal. All right. So let's apply that to your particle in a box problem. If I were to give you this integral in a test, okay, what would be the answer to this question? What's the value of this integral? You should be able to recognize that this is psi for n equals 3, right? And this is going to be psi for n equals 5, right? So that whole thing is just going to be 0. So, oh, this was the homework? You did it the hard way? Okay. So things like this, if you can recognize your functions as being eigenfunction, non-degenerate eigenfunctions of a Hermitian operator, things like this, these types of integrals is a great time saver to be able to recognize these things. Okay.